Welcome to your simple guide to deep learning. We're breaking down the 15 core concepts you need to know. Deep learning is a fascinating field, and we're going to start at the foundation. Deep learning is built on neural networks, inspired by the human brain. They consist of an input layer, hidden layers for processing, and an output layer for the result. Think of it like predicting house prices based on size and location. Activation functions are essentially the on/off switch for a neuron, deciding if it should activate or not. Popular types include ReLU, sigmoid, and TON. Now that we know the basic structure, let's explore how a deep learning model actually learns and makes improvements. Forward propagation is the initial step where input data travels straight through the network layers to produce an output or prediction. The loss function measures exactly how wrong the prediction is compared to the actual result. Common examples are mean squared error and cross entropy. For example, if the prediction is 90 and the actual value is 100, the loss is 10. Backpropagation is how the model learns from its mistakes. It calculates the error and then updates the internal weights of the network to increase accuracy. It's like correcting your answers after checking them. Gradient descent is an optimization technique used to minimize the loss function. It adjusts weights in small steps, aiming to find the lowest error point, similar to walking downhill. Next, let's look at how we measure and optimize a model's performance to ensure it generalizes well. Overfitting happens when a model learns too much, including data noise. Underfitting occurs when it hasn't learned enough. The goal is to find the right balance for optimal performance. Regularization techniques like dropout or L1 per liter 2 are used to prevent overfitting by penalizing complexity. This stops the model from simply memorizing the training data. Training is defined by key terms. An epoch is one full pass of the data. Batch size is the small group of data processed together. An iteration is one update step taken by the model. Now we move on to specialized neural network architectures designed for specific types of data and tasks. Convolutional neural networks, or CNNs, are the experts in image processing. Their applications include face detection and object recognition, like detecting cars on a street. Recurrent neural networks, or RNNs, are specialized for sequence data, such as text and speech. They power text prediction and speech recognition applications. Transfer learning saves significant time by using a model already trained on a massive dataset and applying it to a new, related task. Autoencoders are typically used for data compression, reducing dimensions, and removing noise from data, essentially cleaning up blurry images. Generative models, like generative adversarial networks or GANs, are designed to create new, realistic data, such as generating entirely fake human faces or novel art. Finally, we cover the essential tools used in deep learning and wrap up with a simple core idea. Deep learning frameworks like TensorFlow and PyTorch are the tools that make coding and training these complex models easier and more accessible to everyone. Remember, deep learning is all about learning patterns from data using layered neural networks and improving step by step using calculated errors.